Singapore. Researchers' recent interest is Boltzmann equation and the back conservation law. Today, he's going to talk about wave motion around shark layer and the founding layer. Let us welcome him.
Thank you. It's quite a pleasure to return to Taiwan to give a short break on this subject. I have been working with Taipei on this subject from the hyperbolic conservation law to the Boltzmann equation. Okay, and we have been working for so long. Okay, and it's quite nice to have some survey of what we have been done on this subject. Okay. Today, the title have two components: the wave motion, the shark layer, and actually this fits our background and our interest in the past and also in the future. So what is the shark wave? Okay, it's much easier to start with a picture. You know, okay, if there are bullets fly in the air, you will see, okay, there's a shark wave. Okay, we know it's by our intuition, okay, what the meaning of the shark wave. And now the first mathematical subject about the shark wave is done by Riemann. Everybody knows who's Riemann, okay? And Riemann here, he studied, okay, if a gas on a pipe initially was separated by a membrane, okay, and then if there the density are two different, and when you remove it, and what would happen, okay, and Riemann he derived he's the first one to realize that the solution, okay, we realize a shark wave, okay, is actually a solution with two different constants, and on the way backward, okay, there's some expansion retardant. And he was the first one to mathematically realize the form of weak solution. And so then Riemann started this one in the 18. Then after during the World War II, the subject of shark wave became so important because of the war. And there's a group of people in the Quran Institute study on this subject. And in particular, the Quran Bridges, he summarized. And then there are large development by, for example, the large physics. They're the first one to devise the numerical approximation. Okay, that's become CFD. And the last, okay, he generalized the Riemann's problem. Okay, and then and they become so popular and important, and they used to solve many important problems. And in particular, that the green is his PV solution is so fundamental. And now, and today my talk is based on that. Okay, I want to know, okay, to implement the concept of this conservation law, and how to see how is the connection to the Boltzmann equation, and see how these two fields they are connected to each other. Okay. So let me start from the shark wave, the mathematical equation for shark wave. So what is the shark wave? Okay. And in terms of differential equation, it's a quasi-linear equation. And the most simple quasi-linear equation PDE is a Berger equation. Okay. And so now let me give you use this Berger equation as an example. So when we look at an equation of this form, that this E, that this E means the wave speed. Okay. So you can see from this equation, you see if the value of U is bigger, then wave speed is higher. So now, for example, if we look at some initial value like this, okay, say it's smooth, and here the value U is big, and the wave speed is faster, and the U speed here is small, okay, slower. So eventually the wave in the back, it will faster and compress, the wave is slower. So eventually in the finite time, it forms some singularity, and after a certain time, okay, then the singularity breaks and becomes a shark, okay, eventually like this. Okay. Now, So this is as an example. You see everything is starting from smooth and eventually end up with this one. So you think that shock wave is not man-made. Actually, is a real thing. And then okay, so what the matter, okay, what the difficulty of this subject? So as we know that if we look at a standard initial if we look at a particular problem, okay, so say we look at the same Berger equation, okay, with a fixed initial data, okay, and then we can make up that there are two different solutions, okay, with the same initial data, and the both solutions are weak solution. So this means as an initial value problem for the quasi-linear problem, the solution, the mathematical problem is not well posed. So Peter Last proposed a condition which is you need to have a solution is physical relevant, and he imposed the entropy condition. Okay. And so now here, okay, so he generalized the conservation, the Berger equation into a general nonlinear equation. Okay. And the notion of the entropy condition is that there, if this is a shock wave, there must be some compressibility. That means the wave speed in the behind is faster, okay, in the front is slower. Okay, so have to have a physical relevance. Okay, so then this one will so this okay, so this one will give you the selection principle for physical relevant shock wave. Okay? And but now there's a problem of this notion, because this one is a scalar equation, only one equation, and the most of physical problem is a system of equations. So Lux he generalized his entropy condition as his geometric entropy condition. So okay, so now when we look at the system of conservation law, okay, and now regarding to this Jacob, okay, this flux function, if we look at this Jacobian of this matrix, and this notion of a hyperbolic equation, that means that all the eigenvalue of this Jacobian matrix, they are real, and so this means the wave propagate with a different speed. Okay, so here this is if this dimension n, that's n speed. Okay, and the last entropy condition says that. Okay, so here this s is speed of a shock wave. Okay, and now his notion means that the compressibility means there's n wave enter the shock. Okay, this here this n is a dimension of here. So this means you got the one field enter there. And then you have an n minus wave left the shock. So this is the last entropy condition. So this means essentially only one wave flow compressive here, and all the other wave is just pass through. Okay. And so now here let me give some short break here. So that means all this nonlinear theory of the conservation is based on the concept of all these lines. And now what the meaning of this line? This lines mean wave propagation. So okay, you can identify this one is the Green's function for the linear hyperbolic equation. So okay, so to solve the linear equation, you need to have a better understanding of this wave motion. And now okay, so now we will implement all this structure, okay, to look into the Boltzmann equation. Okay. So now let me give you some brief story about the Boltzmann equation. So let me start from some notion, okay, about the Boltzmann equation. Okay. Okay. So this is quite a long time ago, okay, and then when the Maxwell he find out his Maxwell equation. Okay. So everything is just related to the light. Light is just the wave of the electricity and the magnetic. Okay. And the Crook he want to make an experiment to justify the Maxwell's equation. Okay, so he make such thing a bomb. Okay, and this means everything just like a photon. Okay. And now look here, he put something black and the flat and the black and the white. And so now when the photon go to here is blocked and absorbed. Okay, so you absorb one momentum. And now here, if this is white, and then see here, go there and refract. So here you will receive more momentum. So this means here you got the more momentum difference. So it's supposed to rotate in this direction. But it turns out the experience, the outcome of the experience is wrong. Everything go down, go in this direction. Okay? And then in the year 76, okay, I mean the Queen Victoria, he might Maxwell to explain this phenomenon. But fortunately, the Queen Victoria do not ask him. Okay, so that's Maxwell so happy. Okay, that the Queen do not ask him the difficult question because at that time he do not understand how to explain this one in terms of this Maxwell equation. Okay, and then during this period, okay, Maxwell he just invent notion of the Boltzmann equation. Okay. What is the Boltzmann equation? Okay. We used to start to describe the fluid just by density, momentum, etc. by this microscopic concept. But Boltzmann he introduced the notion of probability. Okay. So this means this F is unknown for the Boltzmann equation. It stands for the probability density of the particle velocity at the given point and multiply the microscopic microscopic density. So this means this means here the F here just say how the distribution of particle velocity, and now all the equation is through the particle collision, and his theorem is so rarefied to the gas just have two collision. Okay, so this means only two particles collide. So then here this operator is a bilinear form. Okay, and the Boltzmann is shown. Okay, and his collision operator is defined this way. Okay, so the particle before collision and after collision. Okay, so then in this collision it makes sure the formula he derived here is ensure the conservation of mass, conservation of momentum, and the conservation of energy is preserved at any given time. And now, okay, and so in here, this collision has two parts. Okay, so after collision, some particle lose its distribution to the other velocity and gain something. Okay, so this is a collision operator. When the Boltzmann introduced this equation, okay, he proved several important things. The first, okay, he said, okay, his collision operator is orthogonal to of these 5 polynomials. Okay, I mean, and this okay, and these 5 polynomials. Okay, this means that this identity. Okay, this one is referred to the conservation of mass, and these 3 okay is particle velocity. Okay, and then the orthogonal to these 3 polynomials means it's related to the conservation of mass, and now this one is the velocity. So this means the conservation of the total energy. Okay, so first, Boltzmann he showed this, okay, and he also showed that if the gas distribution is in equilibrium state, this means that the particle okay is such a distribution is lost and is gained or balanced. Okay, so this means the equilibrium state, and then he proved that if the distribution is an equilibrium state, then it should be in the form as the Gaussian. Okay? So this theta means temperature, okay, and this U means microscopic velocity. Okay? And now here this law is factored out. It means the density. Okay? And he used this notion, and he proved that if this F is the solution of the Boltzmann equation, okay, and he defined this notion, okay, is the H function. And now people realize this one, all the different notion. They say this one is a Hsien entropy function. Okay, and the Boltzmann he showed that the solution of the Boltzmann equation. Okay, then this means that these are H functions. Means entropy, the negative sign of entropy, it always decreasing in time. So Boltzmann he introduced this notion to prove the second law of thermodynamics. Okay, So after this notion of the kinetic equation, okay, then the problem of the crook will be resolved. Okay. So first, here Reynolds he thinks that okay, everything inside here is not really empty. It actually needs a lot of gas. Okay. So so that means in the black and the white was regarded as the gas. The white part it means the cold gas, and the black wire related as the warm gas. Okay. And now inside here is with the same pressure. Okay. So this means it turns out the particle collide with the membrane. It creates the motion. And later, make sure he realized the Reynolds theorem can be applied. Okay. So use this kinetic equation, then he can explain why this van is rotate in this direction. Okay? And the next important mathematical progress on Boltzmann equation is done by Hilbert. Okay? So here he consider this problem. He consider the Boltzmann equation, okay, with a very small number. This is a crucial number. This means the mean free. This kappa is mean the mean free path. Okay? And then he take the power series of the solution of this Boltzmann equation regarding as in terms of this crucial number. Okay? And then it write as a power series. Okay, so it just equate the order of this crucial number. We got a sequence of equation. Okay, and now in here the Boltzmann is show that okay, this collision operator is orthogonal to the collision invariant. Okay, so this means if you want able to solve the problem, okay, so every equation has to be orthogonal to the collision invariant. Okay, so now in order to solving for each order, okay, so now regarding to this equation, okay, then this means this equation here has to be orthogonal to this collision invariant. Okay, so that means it will impose. Okay, so we have 5 collision invariants. Okay, so it will impose 5 equations. Okay, and now this 5 equation is on the density, velocity, and the temperature. Okay? And so his solubility becomes the equation for the Euler equation. So here, but he's the first one to make the real connection between the Boltzmann equation and the gas dynamics. Okay? Now there is even more problem regarding to this. Okay? You might ask whether that the series converge or not. This is one question. And then in the 1963, okay, that there is an important paper by Harold Grant. It referred to the Hilbert expansion. Okay. So now first, okay, in the Hilbert, he do his expansion that he do not refer to the initial data. Okay. He only talk about the solubility. Okay, so only on the equation. So okay, so this means you will need to refer. Okay, you need to input the initial data to the expansion. Is one. And the second, okay, regarding to the most of physical set always have a boundary. Okay? And the Hilbert, his expansion do not encounter with the boundary. Okay? And about the Euler equation, no, the Euler equation always a shock wave. Okay? So that means and they always have a discontinuity. Okay? They will refer to the shock wave. Okay, so now you can think of these are 3 components missing in the Hilbert expansion. Okay, and now so now let me say what is how those will are related to the Boltzmann equation. Okay. So for the shock wave, okay, then this means for the Boltzmann equation, you will need to refer to as shock layer. This means you have a traveling wave solution of connecting to equilibrium state. And then for the boundary layer, then this means okay, you need to import some information. Okay, and that information is not necessary. Okay, consistent with the interior to the PD. And then there's some spatial structure. Okay, there's the boundary layer. Okay, and then of course for the Boltzmann equation, the equation of state is much more than the Euler equation. So okay, and then you, but however, as a mathematical problem, you have freedom to impose arbitrary boundary initial data. Okay, and so how this initial state relate to the rule mechanics. Okay, this is another issue. Okay, so this the graph he proposed. Okay, these three layers in 1963. And actually, we refer to this boundary layer. Okay, there are actually a lot of interesting phenomena. Okay, so that, and this is the Professor Sonnet. Okay, he did a lot on these those way the relationship between the Boltzmann equation and the Euler equation. And for example, that he discovered, okay, if the temperature distribution is not uniform, okay, it will create a thermal creep flow, and such a thing do not appear in the Euler equation or Navier-Stokes equation. This is only is a characteristic for the Boltzmann equation. Okay. And now, and also refer to a different kind of boundary condition that resemble the condensation and the evaporation. Okay, so if you impose the fixed boundary condition, okay, with temperature, and now there's bifurcation refer to your far field. Okay. So that's I mean you have different far field. Okay. Sometimes you have a solution, sometimes you don't have a solution. This is some bifurcation. So this is all some story about the Boltzmann equation I will mention. And so now we come down to the most simple situation. So we look at the comparison. So now in the Hilbert expansion, we know the Boltzmann equation is related to the Euler equation. So we look at the most simple case. So we look at the Boltzmann, the Euler equation around a constant state and linearized. And so here we take the linearized the Boltzmann equation as absolute constraint, and then corresponding to the sound speed of the fiber sphere. So this is the most simple case of the Euler equation. And then we know, okay, for the Euler equation, we know all the way for forward and backward, and the one say here. So we know very precisely about the structure of the linear equation. And then so now we want to make some comparison. So this is structure in Euler equation. And now look at so if we linearize the Boltzmann equation in the very simple setting, the linearized Boltzmann equation around a global Maxwellian, and put the initial data at the delta function, the green function. And so how the wave structure of the Boltzmann equation related to this. And from this, okay, so we can do some basic problem. So we can have a theorem like this. So we use using the collision invariant. Okay, so this is a phi conservation law, okay, to define a micro decomposition. So this is what this three is using the collision invariant to compose to this wave, similar to wave on the Euler equation. Okay, so with this one we define the micro decomposition, and with this micro decomposition, okay, then we have a theorem that is okay. So the solution of the Boltzmann equation, okay, you can write it as a two parts. Okay, so this there's one part. Okay, so this is in the global, okay, global in x and the c. Okay, is we may say as energy, okay, which is decay in time exponential. You can write down solution in one part. Decay in the time. Okay, but it is global. And also you have the other part, okay, corresponding to the long way component. Okay, so, which is within a finite marked region here, okay, and then you have a very precise structure. Okay, okay. So now we can do this. Okay, so we can find the solution. Write it as two parts with a very precise structure in the space and the time variable. But we have another part. Okay, the structure is a global. Okay, in global in x. Okay, and the exponential decay. And now, most of people might be thinking this is enough. Now let me say, this is not sufficient. If you want to go from here to the global, say nonlinear problem, etc. And then this node is an obstacle. So now we need to resolve this component. We need to resolve this this is the global node into a radial with a good structure. So we need to have some different new inputs. Okay, so now we will emit a notion called the mixed lemma. So now let's say so we need to have some realization of the linear collision operator of the Boltzmann equation. So you can write down the linear collision operator at the two parts. It is a multiplication operator, and also an integral operator. And now here is important. Though it looks very naive, but now that's a very good understanding. So now if you write out, so you look so now you just rewrite the Boltzmann equation and the two parts. And then, so now this part is like a transport equation. So now look here, the law of this one. So this one is a differential equation in the space and the time with different velocity. So this part play a role. It brings information from the different position to the same position. So that's mean if I sit in here, this stuff will bring every information from different position to here. And now look here, this operator. And this operator is independent of x. It's just an integration over the C variable. So now this means, so now this operator means if I sit on here, it will act on the particle with a different velocity. So this means that, so here this means, this means that you mix it here. So now look here, so now look at the linear Boltzmann equation, this one and this one. So this means what? So this one means it brings information from different location. And now here, this one, if everything goes to the same location, I just mix it. And now, it's quite interesting. It's in here, now you start with a game here. So now, if I bring here to here and mix it, and then bring here again to mix it, and then we got this mixed lemma. This means that. It means that I can if I so here this operator here this error is mean I mix error time I mix error time. So now here it means that here if I do this mixture 2k times then I can convert the regularity in x variable to the microscopic variable. So this means So this means with this mixture, I can pass the information from the microscopic term to the macroscopic in X. And so now with this small, tiny device, then I can convert this regularity in the C variable to X variable. So this means eventually I can. So previous here, this component, my theorem here is along x2. My previous theorem before, this is along x2. Now I convert it into along infinity. So now everything becomes localized. So once everything goes into this structure, then you got a machinery. So now you got everything you can stay in the point one norm space about the Green's function. Now every machinery is ready. So now we can do the comparison. So now here this picture is the Euler equation. And now for your solution, for the solution of the Boltzmann equation, it shares the same structure globally. So you can think this HEI just means the vector of this vector. And you also here, so now this Y is tell you the diagonal structure, And now if this index R, L, and J are different, this means that you got some off diagonal structure, So this means that the wave outside different mode, okay, it will get an extra decaying rate. Now, let me tell you that this extra decaying rate, it plays the central role to analysis. Without this extra decaying rate, okay, all zero, it cannot do anything. Okay, so now they use this one as a machinery to produce new knowledge. Okay, so first we go look at this machinery to study the invariant manifold, okay, for the stationary Boltzmann equation. Okay, so we look at the equation for the Boltzmann equation without t. Okay, so the stationary solution. Okay, and now just in terms of notion of the ODE. Okay, so now you can write down this one is like an ODE in the X-ray. Okay, and for the ODE, okay, these are some standard notion of stable manifold, unstable manifold, and the center manifold. Okay, okay. So now we look. Okay, so now we look at this one as some constant state. Okay, so we look at the linear Boltzmann equation. Okay, then you got the system of the ODE. Okay. And so now we want to relate it to the notion of the ODE. Okay, so in the ODE, okay, we got some big metric. We can know the projection, okay, to the stable manifold, unstable manifold, etc. For the ODE, you can do it for the finite dimension. But for the Boltzmann equation, okay, so this consists for all variables. So this is an infinite dimensional problem. Okay. So all finite dimensional metric theory is not sufficient. So we need to have notion to define the projection metric. And now the green function, okay. The green function, okay, of the time-dependent problem is the one to play the role, okay, to define the projection metric. So this means, okay, so now though this is the green function for the time-dependent problem, okay. But however, you just, okay, so you need to do some splitting of the flux, okay. Okay, so now you take your green function regarding time, and you integrate over time, okay. And now you can derive this symbol. Okay, now, okay. So first you can say, okay, after you integrate out t, okay, then it's become, okay. This one is called solution of evolution equation. Okay, without, okay, so now you integrate out time, it becomes a solution of the stationary solution. So okay, so this should be a solution of the stationary solution. And now the question is that, okay, you might wonder, okay, whether your integration is integrable or etc. And now we already proved that the off-diagonal term, okay, we get everything with a decaying rate, the decaying structure, okay. So with this decaying structure, okay, you can say this one integration is finite of 1. Okay. And now, okay, so that you solve this thing. And now here to say, okay, so now you need to look at the notion of the stable manifold. The notion of stable manifold is simply say, okay, in terms of x, okay. So you need to show that when x goes to infinity, this one will converge to 0, okay. And because we have all this precise calculation of the green function, okay. So you can show that when x goes to infinity, this goes to 0. Okay. So okay, by these two properties, okay, you can ensure this operator define the projection to the stable manifold. Okay. Okay. So with this one, okay, you can define the projection to the stable manifold, the projection to unstable manifold. Okay. And then you have the center. The center is just consists of the combinations of the collision invariants. Okay. Okay, so now this, okay, so this for the car, if this Mach number, okay, this velocity is far away, this is regular, and now, okay, and now the use of the green function, okay, you even can let this number very small, okay, you can take it to the limit, so you can do the computation, okay, so you can degenerate, the more degenerate, okay, because you can take it to the limit, okay, so you can define, okay, so then when the Mach number, okay, so this number, Mach number